What is up, everyone? It is Mr. Holtz, and today we're going to be looking at some practice problems for drawing Lewis dot structures. Now, after we draw the Lewis dot structures from the given molecular formula, we're also going to look at the VSEPR chart and try and see if we can determine how we can categorize both the molecular geometry and the electron geometry for molecules that have a specified central atom. So let's go ahead and get started. The first molecule that we are going to be looking at has the formula PBr3, okay? So everything we're going to be looking at today is some kind of covalent compound. We're not really going to be drawing Lewis dot structures for ionic compounds. You can do that, but that's not really what we're going to be focusing on because that really has to do with how we form ions and where the valence electrons go. And what we want to be focused on today is how do we represent Lewis dot structures for covalent compounds to show that they're sharing those electrons in that bond. So I'm going to redraw this 3 here. PBr3. Okay, so generally, most of the time, whatever your first atom is in the formula is typically the central atom. Now, in this case, P is the central atom, but the way that you would figure that out is generally it's the most electronegative atom, unless it's a halogen, right? Halogens, and I know my camera's in the way here, the halogens all have 7 valence electrons. So because they can only accept 1 extra valence electron in their valence shell, they typically are not the central atom in molecules. So we'll start with phosphorus, which we find right here. So starting in the 3rd energy level, sodium would be the element with 1 valence electron, and moving over, we would have 2 for magnesium, 3, 4, 5 for phosphorus. So we're going to want to draw our phosphorus atom that has 5 valence electrons. And again, whenever we draw the central atom, my recommendation is to put the valence electrons that we're starting with as dots in one of 4 boxes surrounding the atom. Because generally when we draw Lewis dot structures, if we end up forming 3 bonds, then we'll orient them slightly differently. But we can talk about that after this. But to determine where we're forming those bonds, I like to think of filling these blocks with the valence electrons and going around in a clockwise fashion, similarly to how we drew the electrons in something like the 1s orbital, or actually 1s isn't a good example because there's only 1 subshell, but let's take a look at something like 2p. Okay, remember 2p has 3 subshells. So whenever we were filling it with electrons, we'd put 1 here, and then we'd move over to the next one, right? We aren't going to double fill this until we have to. And that is the same thing that we're going to do with these boxes down here, right? So I put 1 electron in the first subshell, 1 in the second one, 1 in the third one, and then I would start all the way back at the beginning. If I had a 3rd electron, it would go right here. So we're going to kind of look at these boxes that I have the phosphorus surrounded with in a similar fashion. So let's see if we can start drawing these valence electrons here. And because I drew the phosphorus in black, I'm going to represent its valence electrons in black as well. So we just noted that it has 5 valence electrons based on where we find it in the periodic table. So here's 1, 2, 3, 4, and 5. So to fill the octet, whenever we're talking about atoms like this, generally when we do fill the octet, we end up filling these last empty spots with whatever individual electrons we have from other atoms that can fill this box to actually create that covalent bond, right? Because in a covalent bond, we need to have 1 valence electron from both of the participating atoms. So in this problem, we also have 3 bromines, okay? So we have 3 of these bromine atoms. Now, try not to get too confused with all these different colors here. So we're going to want to draw 3 different bromines. Now, when we're looking at the periodic table, again, bromine is right here. We find it in the halogens group. So bromine has 7 valence electrons, which means if I was going to draw a similar orientation for these bromine atoms, then what I would do is draw these boxes here. Actually, I'm not going to draw the boxes, but I'm going to continue to draw the valence electrons around the bromine atom, representing those electrons. Okay, so remember it has 7 valence electrons. So I'll put 1 up here, 1 on the right, 1 on the bottom, one on the left. So there's 4, 5, 6, and 7. So again, if we're thinking of these pairs of electrons as the same as I drew the boxes for phosphorus, there's only one spot around bromine where we can form that covalent bond, okay? Because both of these electrons have filled this box, both of these electrons have filled this box, both of these electrons have filled this box, but this box on the left only has one electron in it. So you guys might be able to notice here that we can fill that box with another electron, but that is the point where we fill that in using a valence electron that's being actually shared in the covalent bond from another atom. Now, because we have 3 of these bromine atoms, we are going to be looking at the same situation 3 different times. Now, to some extent, doing Lewis dot structures is kind of like a puzzle because we want to make sure all of our covalent bonds have 2 electrons in them. And we're going to look at some major points to use to confirm that your Lewis dot structure is correct when you're done drawing it. And we'll take a look at those later. But if you guys recognize that there's an empty spot in this box on the left, then that's going to be the same case for the other 2 bromine atoms as well, right? Because they all have 7 valence electrons, which means after I draw the next 2 bromine atoms we have in this molecule, they'll look exactly the same. Now, what I'm going to do is I'm going to, let's see here. I'm going to see if I can just draw this and drag the whole thing over here. And what you guys will recognize is if I get rid of at least these 2 boxes, that we can form a box that represents a covalent bond with the 2 valence electrons, one here from bromine and one here from phosphorus. Now, that has taken care of the empty spot that we had with this bromine box on the left and the empty spot that we had with this phosphorus on the right. Now, conveniently, we have 2 more bromine atoms. So what we can do is also draw a bromine down at the bottom, and I'm going to fill it with its 1 valence electron at the top. So remember, we still have 6 more. I'm just going to draw them around the outside because it's really important when we're drawing Lewis dot structures, even if the electrons are not going into a covalent bond, if they're just hanging out as a set of lone pairs on the outside, we still want to show that they are there, right? We still want to represent that those valence electrons are being used. They're somewhere in this molecule, and we're going to come back to that in a minute. So here we formed another covalent bond. So let me draw that box here in green. So here's another covalent bond that we have between the second bromine and our phosphorus. And I'm going to do the same thing off to the left with our last bromine atom. So again, we still have 7 valence electrons. So we're going to have 3 sets of lone pairs, just like we have with all the other bromine atoms. And again, I'm going to represent that this box is sharing these electrons, which is why one is black from the phosphorus in every single box, and one is red from the bromine, again, in every single box. Now, this is not going to be your final drawing because, again, we need to show that there are actual covalent bonds being formed here. And the way that we do that is not with these boxes, but it's with the lines that we've seen before. Okay, so I'm going to erase these 2 electrons in all of these bonds. And the way that we represent that there is a covalent bond between these atoms is just with lines that connect them. Now, I do want to keep, whoops, I accidentally erased this line over here. I do want to keep my valence electrons in the lone pair above my phosphorus, just to, again, represent that they are there, because this is our final structure. But before we can confirm that this is our final structure, anytime you finish a valence, anytime you finish drawing a Lewis dot structure, there are 3 major things that we should take into account. So let's take a look at what those are. Part 1, we always want to make sure, and I'm going to start with this after this example for the next few, I'm going to start with looking at these things. So part 1, we want to make sure we have accounted for all of our valence electrons, okay? So account for all valence electrons, okay? That's part 1. So let's check and see if we did that here. Since phosphorus has 5 valence electrons, and we know there's only one phosphorus in this molecule because there's no subscript here, then we know we have a total of 5 valence electrons coming from our phosphorus atom. And in bromine, like we talked about earlier, we know bromine has 7 valence electrons, but keep in mind, we do have a subscript here. So because there are 3 bromine atoms in this molecule, we need to take into account that there are a total of 21 valence electrons just from our bromine atoms, which means that we would have a total of 26 valence. I'm just going to abbreviate it here with VE minus. E minus represents the electrons because, again, electrons have a negative charge. So in this molecule, we should have a total of 26 valence electrons. Now, let's count them up and see how many we have. We have 2 here in the top lone pair. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And again, there are 2 for every single covalent bond. So we just got to 20, 22, 24, 26. So we are good with that, right? We just checked off that we have all 26 valence electrons shown in this Lewis dot structure. And again, that is why we need to make sure that even if these lone pairs are not being utilized for covalent bonds, right? We're either going to have a covalent bond or a lone pair. We still want to show that all of the lone pairs are there. Okay, we can't get rid of any valence electrons. All right. The second major thing that we should be concerned with is have all necessary atoms met the octet. So I said necessary atoms because something like hydrogen, remember if we go back to the periodic table, hydrogen is in the first energy level. And if we go back to thinking about Bohr models of the atom, remember the first energy level around the nucleus can only hold 2 electrons. So hydrogen doesn't actually fill the octet because it can't hold 8 electrons in its valence shell. It can only hold 2. But most of the other ones we'll be dealing with will be meeting the octet. Things like carbon, nitrogen, oxygen, any of the halogens, sulfur, phosphorus, silicon, selenium, all of the kinds of things like that, okay? Because again, because these are covalent bonds, we want to make sure that we are satisfying the octet by filling the valence shell with the valence electrons that are being shared in the covalent bonds. So, for example, I'm going to use the right colors. One of these electrons in this bond is coming from the bromine, right? One of them is coming from the phosphorus. However, because these electrons are both being shared back and forth, we count both the black electron and the red electron as helping to fill the octet for bromine, okay? So when we're counting to see if electrons are filling the octet for all of our atoms, we include both of the electrons that are in a covalent bond because they're still helping as they're being shared back and forth. They're helping to fill the octet for both the bromine and the phosphorus at the same time. So have all necessary atoms met the octet. In this case, because we are dealing with phosphorus and bromine, we do want all of them to meet the octet. So let's just check and see if that happened. So there's 2 here, 4, 6 from our lone pairs, and a total of 2 more from this bond. So yes, this bromine has met the octet with 3 lone pairs and 1 bond. And that's the same for all of these bromine atoms. So all of them have met their octet because they have a total of 6 electrons in their outer lone pairs and 2 extra electrons from that covalent bond. So now let's take a look at phosphorus. Phosphorus has 3 covalent bonds, which account for a total of 6 electrons and 1 lone pair. So 6 plus these 2 meets the 8. So yes, all of these atoms have met the octet. They are all satisfied. Now, the last thing that we need to do, and this is probably the most complicated, is do formal charges add correctly? Now, there are really 2 differences to determine whether they add correctly or not. And the only differences between that are we given a formula for a neutral compound, or are we given a formula for a polyatomic anion or ion in general? And we will look at an example like that before we're done today. But in this case, because formal charges are calculated by formal charge equals the expected valence electrons. So expected valence electrons minus the actual valence electrons. Now, this is where people get confused between talking about formal charges and talking about the octet, okay? The big difference here is in any given covalent bond, both of these electrons count for filling the octet because they're being shared back and forth. However, when we are talking about formal charges, the actual number of valence electrons does not include this electron, because this is not a valence electron from bromine. This black electron is a valence electron from phosphorus. Even though it's being shared back and forth to complete that covalent bond, this is not an electron that we would count when we're taking into account formal charges. So, take a look at this. Because our formal charge for bromine is expected minus actual, again, going back to the periodic table, we expect bromine to have 7 valence electrons because it's a halogen. So we expect it to have 7. Now again, because this electron here from phosphorus does not count as a valence electron from bromine, we can ignore that one when we are calculating how many actual valence electrons do we have around bromine. So this number, this actual valence electrons, is only going to come from our red electrons around any of the bromine atoms, okay? So this bromine actually has 1, 2, 3, 4, 5, 6, and 7 valence electrons, okay? Again, because this black one does not count. So 7 minus 7 is in fact 0. Because that's the same for all of our bromines, we know all of the bromine atoms have a formal charge of 0. We expect them to have 7 valence electrons. In this in this Lewis dot structure, they have 7 valence electrons. So all of them have a formal charge of 0. So now let's check the phosphorus. Okay. Now, again, when we look at the periodic table, we expect phosphorus to have 1, 2, 3, 4, 5 valence electrons. Because we are not going to count any of the red valence electrons from bromine, we can see we have 1, 2 from the lone pairs and 1 from each bond. So we have 1, 2, 3, 4, 5 valence electrons surrounding the phosphorus. Again, we ignore the red ones because they come from different atoms. Now, 5 minus 5, again, is 0. So the formal charge for our phosphorus is, in fact, 0. Now, when we add this all up, technically we would have 0 3 times for all of our bromines, but 0 plus 0 plus 0, still 0, plus our 0 from phosphorus gives us 0, which is good because this molecule here is a neutral compound. Now, the way that we would know whether it's not a neutral compound is if there's a negative charge here or if there's a positive charge. And again, that could be a 1 or a 2 or a 3. And we'll look at an example here later on. Now, this is most commonly found with polyatomic anions. There are some polyatomic cations that we'll look at. One of those will actually be our example, but most of the time when you're dealing with things that are multiple atoms that have a charge, typically it's a negatively charged ion, but when that happens, you have to take into account those electrons. Now in this case, because PBr3 is a neutral compound, we do want to make sure that all of our charges add up to 0, because this confirms for us that we are in fact dealing with a neutral compound. So we just confirmed the third box. Do we meet all the formal charges? Yes, we do. We have a neutral compound. Therefore, this, and again, just so you're aware, we don't actually show the electrons in the covalent bond. I was just emphasizing what we needed to know there. So this right here would be the final Lewis dot structure for the formula PBr3. Okay? Cool. let's move on. Number 2. So molecule number 2 that we will be looking at is N2H2. Okay, now this one's a little bit more difficult. So in this case, again, nitrogen is more electronegative than hydrogen, so I would start with nitrogen as a central atom. However, there's 2 nitrogens here, so we won't necessarily have a central atom like we did in this example because phosphorus is in the middle of the molecule. Now, because there's 2 nitrogens, we don't necessarily know what it's going to look like, right? It could be like this. We could have an N on the side and H's around here, but that's our whole molecule, so we'd have to think of something else. Now, one trick that I want to share with you guys before we keep moving is most of the time, and by most of the time I mean like 95% of the time, if you look at this table here, this will show you what you should expect in your final structure. So for hydrogen, typically we only form 1 bond and 0 lone pairs, again because hydrogen can only hold 2 valence electrons in its valence shell. Carbon typically forms 4 bonds and 0 lone pairs. Nitrogen tends to form 3 bonds and 1 lone pair. Oxygen forms 2 bonds and 2 lone pairs. And all of our halogens, just like we saw in the last example, form 1 bond with 3 lone pairs. And that's exactly what we saw with our bromines here, right? They all formed 3 lone pairs and 1 bond. So in this case, because we have 2 nitrogens, we would expect them to form 3 bonds each with 1 lone pair. Now, what I'm going to want to take into account before we start drawing this is nitrogen. Oh, not sure what just happened there. Nitrogen, when we're looking at the periodic table, is just above phosphorus. So just like with the example last one, in the last problem, phosphorus and nitrogen both have 5 valence electrons. So it has 5 valence electrons. However, because we have 2 of them here, let's take that into account. So we would expect to have a total of 10 valence electrons from both of our nitrogens. Hydrogen has 1 valence electron. Again, there are 2 of them from this subscript. So we expect there to be, whoops, not 12, 2 valence electrons from all of our hydrogen atoms. Now, if we add this up, we expect there to be a total of 12 valence electrons from or in our final Lewis dot structure. So let's go ahead and see if we can play around with this. Now, generally, when you see something that can form multiple bonds next to a hydrogen, hydrogen's almost always going to be on the outside, right? It can only form 1 bond. So it's not like it's going to attach in the center to multiple things to keep them together because it can only make 1 covalent bond. So what I'm going to do is I'm going to draw a nitrogen here and have it form a bond with hydrogen. Okay, so this will kind of be the outside on the right side of our molecule. Now, I don't know exactly what's going to happen here, so I'm just going to draw 1 bond between this nitrogen. And again, we have to assume that there are electrons being represented within these bonds. Okay, so this bond that I'm hovering over here is containing 1 valence electron from the nitrogen on the left and 1 valence electron from the nitrogen on the right. Now, typically, when you have molecules that have the same number of atoms, they really like to be symmetrical. Or when you have an opportunity to allow that, regardless of whether or not the subscripts are the same, molecules really like to be symmetrical. I'm going to draw the other hydrogen over here. Now, if we're counting the total number of electrons, we have 2 in this bond, 2 in this bond, and 2 in this bond, which is only 6 valence electrons. So I've accounted for all my atoms, which is great, but I don't yet have all of my valence electrons. And again, generally, nitrogen likes to form 3 bonds and 1 lone pair because it has 5 valence electrons. So if you drew that, it would look something like this. 1, 2, 3, 4, and 5. So if we go back to what we tried at the beginning of problem 1, this box at the top of nitrogen is completely filled with electrons. We can't add anything else there. So we can't form a bond there, right? Because these boxes are empty, or at least partially empty, we can fill them, all right? Now, both of these nitrogens currently have 2 covalent bonds. right? One on the left of each and one on the right of each. Since they only want to form one more bond and they both like to have one lone pair, I'm just going to draw the lone pairs up here to represent them. And this is where things get a little tricky because this problem is doing something that we haven't seen before. Now, what's going to happen is we're going to actually form an extra bond between the nitrogens. So if you count them all up, we still have 1, 2, 3 bonds for both of the nitrogens and one lone pair for both of the nitrogens. Now, to make sure this is correct, let's go back and actually, I'm going to keep that there. Let's count how many total valence electrons did we end up with here. Well, if we have 2 from this bond, 2 from this bond, 2 from the bond on the top, 2 from the bond on the bottom, 2 from this lone pair, and 2 from this lone pair, we have a total of 2, 4, 6, 8, 10, 12, which is exactly what we expected to have, which is awesome. And again, our nitrogens here have all formed 3 bonds and 1 lone pair, and all of our hydrogens have formed 1 bond and 0 lone pairs. But again, this is kind of like figuring out the puzzle pieces, because if you drew both nitrogens out, it would be, oh, that's not what I meant to do. It would be the same thing for both of them, right? So let me see if I can copy and paste this. All right, we've got 2. Can I not move that now? Okay, great. This isn't working very well. Okay, I'm just going to draw it. So again, we have 1, 2, 3, 4, 5. So this looks just like the nitrogen that we drew on the left. Now, because we can fill 3 of these boxes here, we know one of them is going to be filled with a hydrogen for each one. So let's say we filled this hydrogen right here and this hydrogen right here. There are still 2 boxes that need to be filled. One right here and one right here. Now, we haven't really gotten into talking about how double and triple bonds form yet, but just know that if you get a situation like this, these 2 electrons can share this box here. So that's how we form 1 bond, and these 2 electrons can share both of their boxes. So that's how we form our second covalent bond. Now, I know it looks kind of funky because both of these bonds are being formed across where we would expect 1 bond to form, but we'll talk about what that looks like 3-dimensionally later on. So just know that you can form double and triple bonds between atoms if that is needed to get to your final number of valence electrons, because sometimes that's needed, especially if we don't have a ton of valence electrons. Okay. So we've accounted for all of our valence electrons. Now let's see if these atoms have filled their octet. Well, nitrogen is something that will be filling the octet. So if we count them all up, we have 2 electrons here, 2 from the lone pair, and 2 from each of these bonds. So we have 2, 4, 6, 8. And it's the same thing for both nitrogens since this molecule is symmetrical. So we have met the octet, which is great. Now again, hydrogen only wants to form 1 bond because it has 2 spots for valence electrons in its energy level. Now, let's take a brief look at some VSEPR structures and see if we can figure this out. Now, when we're looking at this VSEPR chart, we need to keep in mind that this is really meant to analyze atoms that have a central atom. Now, or molecules that have a central atom. Now, looking at what we have right here, it's not extremely obvious what the central atom is because there's nothing actually in the center, right? Both of these nitrogens are in the middle, but neither one of them is the central part of this molecule. So because they have the same structure, we can just think of either of the nitrogens as our central atom here. Now, the way that we're going to look at this is when you determine what your central atom is, we want to know 2 things: how many lone pairs are around it and how many bonds are around it, or how many domains. And a domain here would be nitrogen is attached to it. That is 1 domain. Even though it's double bonded, it's the same atom. Okay, this nitrogen is the same atom being bonded to our first nitrogen. So we count this as 1 domain or 1 location where there's something going on connecting to this nitrogen, okay? This hydrogen is also considered a domain, something else that's being bonded to it, and these lone pairs count as a domain or something that's going on around our specified atom. Now, these are a little bit different in terms of how we categorize them because they're not covalent bonds, they're a lone pair. But in this case, we have nitrogen with 2 atoms bonded to it and 1 lone pair. So we would count this as what we call AX2E. And we find that right here, AX2E, because we're bonded to 2 things and we have 1 lone pair. So the E right here refers to lone pairs. So how many lone pairs do we have around the atom? And you can see if you look at this, there are options where we have 2 lone pairs or 3 lone pairs or 1 or even 0. And the X refers to outside bonded atoms. So in this case, the nitrogen on the right and the hydrogen on the left, outside bonded atoms. And the A just refers to our central atom. So how many things are happening that are either lone pairs or bonds to that central atom, right? What's going on around the atom that we care about. Now, because both of these nitrogens are symmetrical, the structure, or our VSEPR structure here, would be AX2E for both of them, okay? Now, what that means is that our molecular shape is bent, so it tells us how the molecule is oriented in 3-dimensional shape, or 3-dimensional space, and the electron geometry, because it includes any lone pairs that we have, is trigonal planar. And we'll talk more about that later on. So this right here would be your final Lewis dot structure for this molecule, okay? So typically nitrogen can form single bonds, double bonds, and triple bonds, but regardless of what kinds of bonds it forms, it's almost always going to want 3 bonds and 1 lone pair. But we will look at an example later where that is not the case. Okay, moving on to number 3. Now this one again does not really have a central atom, but this is a really good example. And if you ever take organic chemistry, this will help you out a lot, because organic chemistry is all about forming covalent bonds and large molecules with things like carbon, hydrogen, oxygen, and nitrogen. So what we're looking at here is CH3OH. Now this is actually a molecule called methanol, which is a flammable liquid, and it's something you don't want to ingest because it'll actually make you go blind, but we'll talk about that later. Okay, so again, generally, especially if you have carbon as the first atom, that's pretty much always going to be your central atom, because carbon, if you go back to this chart, can actually form the most amount of bonds of any atom that we have. So I'm just going to put carbon in the center, and because carbon has 4 valence electrons, I'm going to draw those 4 valence electrons around this atom. Now, conveniently, it's actually written in this way to be really specific, right? Because this is the same thing as saying CH4O, right? I just took this hydrogen and combined it here so that they have the same subscript. However, if you see molecules written out like this, it's actually really helpful because it kind of segments out different parts of the molecule for us. So what I see here is CH3 separate from the OH. Even though they're in the same molecule, there's a reason this H is at the end instead of incorporated into its own subscript, okay? So what I'm going to do is I'm going to start with the 3 H's out here on the left side of my hydrogen, and again, or of my carbon, excuse me. So again, hydrogen only has 1 valence electron. So we can think of all of these electrons forming covalent bonds right here. Now, we still have a bonding location here, but keep in mind, it was written OH for a reason. So I'm going to draw the oxygen on the right side of the carbon just because that's how it was shown to us in this molecule or in this formula. So here's my oxygen. Now, how many valence electrons does oxygen have? Well, if you look at the periodic table, it's 2 after carbon and 2 before neon. So you could count from the left, but oxygen ends up having 6 valence electrons. So I'm going to draw 1, 2, 3, 4, 5, 6. Okay, so here are 6 valence electrons. Again, this group up at the top has formed a lone pair, so we're going to leave them there, and they can't form a bond now. The group on the right has also formed a lone pair because there's no other space there. Now, conveniently, we can form a bond right here with these last electrons that are left in between the carbon and the oxygen. So the only thing we have left to fill in is our last hydrogen, which again only has 1 lone pair. So we could finish our bond down at the bottom, and what we end up with is, if we drew this whole thing out, we have carbon, oxygen, and I'm going to draw the lone pairs in last. So we have 3 hydrogens attached to the carbon, 1 hydrogen attached to the oxygen, and then we have 2 lone pairs also around the oxygen. So let's make sure that we've accounted for the 3 major things in this molecule. Okay, so carbon has 4 valence electrons. There's 1 carbon in this atom, so we expect 4 valence electrons to come from our carbon atoms in this molecule. Hydrogen has 1 valence electron. We have a total of 4 of those in this molecule. So again, 4 valence electrons from all of our hydrogen atoms. And oxygen has 6 valence electrons, but there's only 1 of those. So we expect to have 6 valence electrons from oxygen. Now, if we add these all up, we get a total of 14 valence electrons. So the question is, do we have 14 valence electrons in this molecule? Well, if this is our final structure, or at least our intermediate final structure before we confirm that it's legit, we have 2 from every bond and 2 from each set of lone pairs. So we have 2, 4, 6, 8, 10, 12, 14. Boom. Awesome. We do have 14 valence electrons in this structure. Now, has everything that we need to met the octet? Well, the only 2 atoms here that are actually filling the octet are going to be carbon and oxygen, and we include the electrons in all of the bonds to do that. So around carbon, we have 4 bonds, and in every bond there are 2 electrons, so 4 times 2 is 8. Carbon is satisfied. Oxygen has 2 bonds, which each have 2 electrons in them, and 2 lone pairs, which again have each 2 electrons in them. So 2, 4, 6, 8. Oxygen has also met the octet. That is a happy atom. Now again, the hydrogens only form 1 bond each. So the last thing we should be taking into account here is the formal charges of all of our atoms. Now, again, basically when we do that, we split the electrons in half from each bond, because when we're dealing with formal charges, we only count the valence electrons that each individual atom brought with itself. So all of the hydrogens are only in 1 bond, so they only account for 1 of the valence electrons in each of those bonds. Because we expect hydrogen to have 1 valence electron, and in this entire structure, each of these hydrogens only has 1 valence electron, all of their formal charges are 0. So hydrogen is sitting pretty with a formal charge of 0 in all of these atoms. Carbon has 1, 2, 3, 4 valence electrons around it. We expect it to have 4, so carbon is happy. Carbon has a formal charge of 0. Now oxygen has 1, 2, and all of the total 4 from the lone pairs. So oxygen has a total of 1, 2, 3, 4, 5, 6. But again, oxygen, we expect to have 6 valence electrons. Therefore, oxygen also has a formal charge of 0. That is a happy molecule. So we are good there. Now, there's not really another specified central atom in this molecule, so it's difficult to apply VSEPR structure theory to this. But if you wanted, you could isolate and say, okay, my oxygen, we're going to count as the central atom here. And then you can figure out how many different domains are there around it. In this case, we would have 1 lone pair, 2 lone pairs, 3 from a bond, and 4 from a bond. So because there are 2 lone pairs and 2 bonds around our oxygen, we would count this as AX2E2, which is right here, AX2E2 for a total of 4 domains. This is exactly how we draw oxygens, just in the center, right? 2 things that are attached and 2 lone pairs around it. So its molecular shape would be bent and its electron geometry would be tetrahedral, okay? Moving on. All right, let's take a look at this one. So now we're actually running into a problem. What is this, problem number 3? Problem number 4. Okay, problem number 4. We are dealing with NO2 minus. Now, this is a great example of a polyatomic anion. So this is something called nitrite. So if you look at your polyatomic anion chart, it should be on there. Now, when we're totaling up the number of valence electrons for this molecule, we need to take into account the fact that there is a negative charge here, because that negative charge tells us there's 1 extra valence electron somewhere in this molecule, okay? So nitrogen, if we're looking at the periodic table, has 5 valence electrons. There's only 1 nitrogen in this molecule, so we expect 5 valence electrons to come from our nitrogen. The oxygens have 6 valence electrons, but there are 2 of them from this subscript right here. So we expect 12 valence electrons from our oxygens, which is a total of 17. However, because we still have that negative charge here, and electrons have a negative charge, this negative on the molecule shows us that we need to account for 1 extra valence electron. So we should have a total of 18 when we are done with this molecule, okay? Now in this case, oxygen is slightly more electronegative than nitrogen. However, because there's only 1 nitrogen and it tends to form more bonds than the oxygens do, it's safe to assume that the nitrogen will be the atom in the center of our molecule here. So here is my nitrogen, and this problem is actually going to be a little bit different because I'm going to talk about something that's kind of new to us. So nitrogen has 1, 2, 3, 4, 5 valence electrons. Now, what you might notice here is that there are 3 boxes that need to be filled, and we only have 2 other atoms in this molecule. Now, this is going to be similar to what we saw in problem number 2, right? When we don't have an option for forming 4 bonds around a molecule or forming 4 total things, whether that's bonds or lone pairs, sometimes we need to form multiple bonds between 2 atoms. So when we draw out oxygen, and oxygen has 6 valence electrons, we can see that there are only 2 boxes around the oxygen that need to be filled. However, we still need to take our negative charge into account. So what I'm going to do is I'm going to put an electron or an oxygen on both sides of this nitrogen, and then we'll go from there. So here's an oxygen, and we're still going to have 1 electron that has yet to be filled with anything. So I took 1 of these electrons and put it in this box, and 1 is still by itself. Here's our other oxygen. I'm taking 1 of the individual electrons and filling that box with it, and there is 1 at the bottom. Now, if we count up the total amount of electrons we have here, we only have 2, 4, 6, 8, 10, 12, 14, 16 from these 2 here, and 17 from the one underneath this oxygen, and you can count them as well. Because we're missing 1, we need to figure out where to put 1 of these last electrons. Now, what I'm going to do is I am going to move this electron from the bottom of the nitrogen and see if we can form an extra bond right here. So we already have a bond formed between the oxygen on the left and the nitrogen from this box right here. And we formed one down below. So this is going to be, again, an example where we're forming a double bond. But the question is, what's going on right here? Because we cannot leave this box unfilled because we can't have individual electrons. It doesn't happen, or at least for what we're talking about in this class, it doesn't happen, okay? But we have not added our 18th electron yet. So I'm just going to add in an electron here to represent where this negative charge is coming from, okay? Because we have an extra electron. Now, if I wanted to draw this a little prettier, we have one bond here between the oxygen and the nitrogen on the right, but we have 3 sets of lone pairs, okay? 2 of them already came from the oxygen, and 1 of them is counting for the negative charge electron that we have. Now I've formed 2 bonds between the nitrogen and the oxygen on the left. Still want to take my lone pairs into account up top, and here is this oxygen, and it still has 1, 2 lone pairs outside. So I'm going to put them up top and down below. Now, let's take a look at all of our, actually, let's take a look at the electrons, then the octet, then our formal charges, okay? So we have 2, 4, 6, 8, 10, 12, 14, 16, 18. So we've accounted for all of our electrons, which is great. Have we met the octet? Well, all 3 of these atoms are atoms that want to fill the octet. So have they all done so? The oxygen on the left has 2, 4, 6, 8 electrons around it. So yes, this oxygen has, it's happy. Nitrogen has 2, 4, 6 from bonds, 8, so a total of 8 from 2 from that lone pair. Nitrogen is happy. And this oxygen on the right has 2, 4, 6, 8. So yes, all of these atoms have met the octet. They are satisfied in that regard. Now, let's take a look at formal charges. Nitrogen, we expect it to have 5 valence electrons. Because again, we're only counting 1 electron from each bond, we count 1 here, 2, 3. I'm not going to draw them because I want to keep my structure looking pretty. 3, 4, 5. So nitrogen, 5 minus 5 is 0. I know I'm writing this kind of weird, but I'm trying to apply it vertically. So nitrogen is, in fact, satisfied, okay? It has a formal charge of 0. 5 minus 5 is 0. Now let's look at the oxygen on the left. We expect it to have 6 valence electrons, and again, around it, it has 2, 4, 1 from this bond, 1 from this bond, so 2, 4, 5, 6. This oxygen on the left has a formal charge of 0. Great. What about the oxygen on the right? 2, 4, 6, and 1 from this bond, so it actually has 7. But again, we expect it to have 6. 6 minus 7 gives us a negative 1. So if we add up all of these values, 0 plus 0 plus negative 1 gives us a total overall charge for this molecule of negative 1, which in fact is exactly what we want, because we can see right here that this molecule has a negative charge on it because it is a polyatomic anion. So this is a scenario where it is okay to have a formal charge of something other than 0, because we need that to end up with the Lewis dot structure matching the actual molecular formula for this compound. So, is this your final answer? Yes, kind of. Because how do you know that the oxygen on the left is the one that deserves 2 bonds compared to the one on the right? Why can I not draw the molecule like this? I'm going to have 1 bond with 3 lone pairs around the oxygen on the left. Here's our nitrogen again. And instead, I'm going to flip these opposite. So now I have 2 bonds between the nitrogen and the oxygen on the right, and now the oxygen on the right is going to have 2 lone pairs. Okay, so you guys can see that I kind of just flip-flopped this oxygen with this oxygen. Now, these are not the same molecule, right? They're representing the same formula, but drawing the molecule like we have on the left compared to what we have on the right represents two different organizations of where we have these electrons distributed, right? Showing that there's a -1 charge on the oxygen on the right in our first drawn molecule is different than showing that on the oxygen on the left in the molecule that we drew the second time. Now, both of these molecules are technically correct. However, when you are asked to draw a molecule that can be drawn in multiple different ways, meaning that sometimes we could have a double bond with the oxygen on the left, and sometimes we can have a double bond with the oxygen on the right, this is what is called resonance. So these are called resonance structures because they both accurately represent everything that we need in this molecule, meaning they all meet the octet correctly, they both have 18 valence electrons, and they both give us a total overall charge on the molecule of -1. So when you are asked to draw the Lewis dot structure for something like nitrite, you would need to draw both of these compounds, because both of these are technically ways that we can orient the electrons within the molecule NO2. And we'll talk more about this in class. But just know that if you can draw them in multiple situations where there's a molecule that looks just like another one, but there's some things moved around, then you need to draw both of the structures, okay? Because there's a difference between having the double bond with the oxygen on the right versus having the double bond with the oxygen on the left. Okay, they're different orientations of where we find the electrons, even though both of these are still correct pictures of this molecule. Okay? Now, in this case, because it doesn't really matter which one of these we're looking at, and we have a specified central atom, right? Nitrogen's the only thing that is actually in the center. We can, in fact, draw or talk about the VSEPR theory for this molecule, regardless of which one we're looking at, either the one on the left or the one on the right. But either way, nitrogen is in the center. It has two atoms bonded to it, right? Both of them are oxygen, and it has one lone pair. So the way that we would write this out is AX2E, okay? So AX2E, total of 3 domains. That's what we see as this nitrogen right here, because we have two bonds, or two bonded atoms, right? Still has 3 bonds, but one of them's bonded twice. So it counts as one bonded atom with one lone pair. Now, obviously, there's still the second oxygen, so there's a total of 2 bonded atoms. That gives us a molecular shape that is bent and an electron geometry that is trigonal planar. So I think that's the last example we're going to go over for today. But if this was helpful for you guys, please make sure you hit that like and subscribe button. It's helpful for me to know how useful this is for all of you. And if you have any questions, please toss them in the chat, or you can bring them to class. But hopefully this was helpful in giving you guys some practice at drawing Lewis dot structures and applying the VSEPR theory to those structures depending on what our central atom is. So I hope that helped. I hope you guys have a great rest of your day. Make sure you hit that like and subscribe, and I'll see you in class.